Right, hi, Mr. Townsend here. Hey, I've made this video for you to use as revision to go over the major functional groups and the reactions that they undergo for Year 13 Organic Chemistry. If you go through this video and watch it a couple of times and try and memorise the important things that I say, it should help you in your organic chemistry paper at the end of the year. Okay, let's look at the first functional group, that's alkenes. Now, first important thing about alkenes is that we've got this double bond functional group. So any organic compound that has the double bond between the two carbons is going to be an alkene. Now this can, excuse me, you can be an alkene when you have another function group as well, but anything that has a double bond carbon is an alkene. This alkene that we've got here has its double bond on the first carbon, so it's going to be called pent-1-ene. Okay, let's look at some of the characteristic reactions that alkenes undergo. Now, alkenes are known for their ability to undergo addition reactions. Because they have two bonds here between these two carbons, one of the bonds can break and we can add new atoms or parts of molecules to it. So addition reactions. First type of addition reaction we've got is this one here. So we're adding the reagent concentrated sulfuric acid and H2O as well. And what we're going to do here is we're going to end up adding, so if we take this double bond here, we add this reagent, we're going to end up adding the alcohol and the H across where the double bond was, or the OH and the H making an alcohol. Okay, second type of addition reaction we have here is what's called hydrogenation. That's when a hydrogen is added on each carbon here from the double bond. Okay, so we take the double bond, we've got the hydrogen with a nickel catalyst, and we produce an alkane. Third type of reaction here is what we call halogenation, because we're adding an halogen again to the double bond. This is where the action is taking place. Notice here, this one is actually following Markovnikov's rule. You might remember that from last year. So we have a hydrogen added to the carbon that has the most hydrogens already. That's this carbon on the right, it already has two. And we have the chlorine is added to the other carbon. Okay, let's have a look at the next slide. Okay, that's the alkenes. So now we look at the alcohols. Now alkenes we did last year, alcohols we did last year as well, but there's a couple of new things, especially this year. Remember, we can recognise alcohols because they will have the functional group OH. In this case, this is a primary alcohol because it's attached to the end carbon. Remembering that a secondary alcohol would be attached to a carbon that has two other carbons joined to it. In this case here, this is called pentan-1-ol, as the OH is attached to the first carbon. Right, the first type of reaction that alcohols undergo that we're going to go over here is oxidation. Now, oxidation here, we're going to use the oxidizing agent dichromate, acidified dichromate, Cr2O72-. We could have used the another reagent called acidified permanganate, which is Mn O4- /H+. But look, we'll just, if we acidify, so if we add the acidified permanganate, what happens is we get this intermediate product made here. This intermediate product is what we call an aldehyde. It has an aldehyde functional group. And if we continue to have this acidified dichromate in the solution, we're going to keep reacting this aldehyde, and we're going to turn it into the end product here, which is carboxylic acid. So really what happens when we oxidize an alcohol, a primary alcohol, under what we call reflux conditions. That's conditions where they're forced to react through to completion, we make a carboxylic acid. Incidentally, if it had been a secondary alcohol and we'd oxidized it, it would have turned into a ketone. Substitution. Right, what we can do is we can take this OH functional group here and we can substitute it by adding concentrated hydrochloric acid. This is actually, usually the concentrated hydrochloric acid has zinc chloride as well with it, but lately in the NCA examinations they've just put it down as HCl or concentrated HCl. So what happens is the chlorine from the HCl here is going to replace or substitute the OH, and it's going to make this haloalkane. Notice with all of these reactions, all the actions taking place at the functional group at that point in this organic molecule. So when we substitute, that is the point that changes. Okay, so the last type of reaction an alcohol undergoes is elimination. Now, elimination for alcohols involves us adding concentrated sulfuric acid. Okay, concentrated sulfuric acid loves to rip off water from molecules. So in this case, it's going to take away the OH here and the adjacent hydrogen. It's going to take both of them away to remove our water, okay, and it's going to make what we call an alkene. Okay, so that's alcohols. These are the characteristic, most important reactions that we need to know. Okay, next type of functional group that we have here are haloalkanes. Now, haloalkanes are, here's an example of a haloalkane, a molecule that contains a halogen. Now, halogen is not just a chlorine atom. It could be a bromine, a fluorine, or an iodine. Okay, in this case it's a chlorine, and in my example is going to use a chlorine, but you can swap this chlorine out with a fluorine, a bromine, or an iodine. In this case this is called 2-chloropentane. Okay, the naming convention here. Okay, haloalkanes. Characteristically, they undergo substitution reactions. This is the type of reactions that haloalkanes mostly undergo. So here's our first type here. We're adding, we have our haloalkane. In this case, it's a chlorine. Okay, remember it could be a fluorine, an iodine, or a bromine. I'm adding ammonia to it. Okay, so I'm adding ammonia to this, and what's going to happen is it's going to substitute the chlorine here. So it's going to make NH2, right, which is an amine. There's actually going to be another byproduct. I haven't written that down here, but there's going to be HCl made as well. Okay, so next, now we have another substitution reaction, but there's another type of reaction that happens here. It's called a competing reaction. When, let me just get these down. When I add hydroxide, and lots of times when we add hydroxide, it's going to be sodium hydroxide or potassium hydroxide. That's what's going to be written down in the question. And if it's aqueous, okay, what it's going to do is the OH is going to replace the chlorine here. So the OH replaces the chlorine, and we get an OH, what we call an alcohol, because we've got the OH functional group. However, this is the major product, and this means this is the product that happens most of the time when we produce an alcohol. There is a minor product that's produced at the same time as this, and this is an alkene. Now, actually, if you take the same molecule, here it is, with the chlorine functional group, this haloalkane, and you add an OH minus that's dissolved in alcohol or alcoholic, remember again it could be sodium hydroxide or potassium hydroxide, the major product when it's dissolved in alcohol is an alkene. So these two are said to be competing reactions, because for the substitution reaction, you would have OH minus dissolved in aqueous, and it would produce an alcohol as the major product, but it would actually produce an alkene as the minor product. And on the other hand, if we had the same reaction with the OH minus dissolved in alcohol, we get the alkene as the major product, and we could get the alcohol as the minor product. Hence, we've got this heading above at the top here that says these are competing reactions. This is actually a really important reaction, and it occurs quite often in the organic chemistry exam. Okay, amines. Amines, as the name suggests, there's the functional group of the amine. Okay, the name comes from the ammonia. So we've got amine functional group here. We name it 2-aminopentane. Amine has a physical property, a characteristic physical property, that when it reacts with water, okay, when this functional group reacts with water, water donates a proton to it, or it accepts a proton from water. So this is what we would call a weak base. Okay, it's quite a weak base, but it's a weak base. It reacts with water, and it turns into this ion here, plus hydroxide ions. This hydroxide ion is written HO instead of OH, but that's irrelevant. It doesn't matter which way around it's written. Incidentally, if you put an amine in water, because it's a weak base, it would make the OH ions, and then you could test it, say with litmus paper or universal indicator, and it would make the paper go blue or the universal indicator go blue, and that would be a test to see whether an amine was present. Right. Producing an amide. Okay, so we can take an amine and we can make an amide from that. How do we do that? What we do is we've got the amine functional group here. To make an amide, we can react it with what's called an acid chloride here. Okay, and the acid chloride will, this is really reactive functional group in acid chloride. It's going to join to the nitrogen here, and the chlorine from here and a hydrogen from here are going to take off and be by themselves and make HCl over the right here. Aldehydes. Right. Aldehyde, here it is. This is has this functional group, a C double bond OH. Just learn to recognise that it could just have an H just coming off the end here, or it could just be written COH. Okay. This aldehydes have the end of anal, so this is pentanal. Ketones are similar to aldehydes. Aldehydes always have a functional group on the end of a molecule. The ketones can have the functional group anywhere within the middle of the molecule. They have this carbon double bond oxygen functional group. Because it can be anywhere within the middle of a molecule, a ketone is going to have a number to say where this carbon double bond oxygen functional group is. In this case, it's pentan 2-one. Just looking back at the aldehydes, because an aldehyde is always at the end of a function of a carbon chain, it never has to have a number to say where it is. Okay, ketones don't really undergo any reactions that we look at in year 13 chemistry, but aldehydes do. Aldehydes are partially oxidized, so we can oxidize them one more step. Okay, so here we go. We can take this aldehyde functional group and oxidize it with here acidified dichromate, and we can make a carboxylic acid. Right, carboxylic acids. Carboxylic acids, pretty easy to recognise. We've got this big chunky carbon double bond oxygen OH group at the end. Sometimes it's just written COOH or CO2H. Okay, really easy to name. You don't need to put the numbers in here as either. You just have to say how many carbons are on the chain. So in this case it's pentanoic acid. Okay. reactions with water. Okay, because this is an acid, this is an organic acid. Now, all organic acids, or just about all organic acids, are weak acids. So what this is going to do, it's going to react with water, and it's going to produce, so it's going to dissociate, it's going to be at equilibrium, okay, so it's going to react with water. Basically it's going to donate its proton to the water, and it's going to make this carboxylate ion here. Okay, notice this has lost its hydrogen, so now it's an O minus here. Okay, carboxylic acids also like, or also can undergo substitution if we have the right conditions. In this case, the right conditions would be adding PCl5. However, it would also react with PCl3 and thionyl chloride, which is SOCl2. Basically what it's doing is this molecule has lots of chlorines, and they're freely available to substitute with the OH to produce this acid chloride here. Okay, the acid chloride functional group. Okay, last reaction that we're interested in with carboxylic acid is esterification. Esterification, okay, we've got the carboxylic acid functional group, and we can react it with the OH functional group from an alcohol. We need to have concentrated sulfuric acid to remove the OH and a hydrogen, to remove a water from the molecule, so that these two will join together and produce this ester bond here. Okay, right, acid chloride. So acid chloride has the functional group C double bond OCl, and we name it pentanoyl chloride. Okay, pentanoyl chloride. This acid chloride is characteristically like to undergo substitution reactions, just like haloalkanes do. Okay, these chlorine atoms at the end of organic molecules are prone to be substituted. So first type of substitution we can have here is we can replace the OH from water with the Cl. Now this is a very vigorous reaction. If you add water to an acid chloride, it will react very quickly, and it makes carboxylic acid and hydrochloric acid. So it makes a very acidic solution afterwards. So if you add water to an acid chloride, you can test the solution afterwards, and if it turns blue litmus red, or if it turns universally or indicator red, you're going to know that it could possibly be an acid chloride. It's like a good test for it. Okay, now this, let's just click through this carboxylic acid made here. Another substitution reaction, we can add ammonia to our acid chloride, and the NH2 will take the place of the Cl. Okay, notice again we've got the hydrochloric acid byproduct here. So we've got our acid chloride functional group. NH3 is going to substitute where the chlorine was, and one of the hydrogens is going to take off with the chlorine, and we're going to get this amide functional group. Okay, as well as substitution, we can have a type of reaction that's called condensation. Condensation is where we add two molecules together and we remove a smaller molecule, either water or HCl. In this case we're adding okay, we've got the acid chloride functional group and the alcohol functional group. And what's going to happen is the Cl from here and the H from here are going to take off, and what we're going to be left with is these two ends are going to join together and make our ester. Notice this alcohol here, I've just flipped it round so that it joins up to make this ester. Okay, another type of condensation reaction that acid chlorides readily undergo are reactions with amines, okay, to make a secondary amide. So this reaction happens really easily. Incidentally, a carboxylic acid will not react with an amine in the same way. If I was to have a carboxylic acid react with the amine, what would actually happen is, because the carboxylic acid is an acid, and the amine is a weak base, they carry out an acid-base reaction instead of this type of organic reaction where they produce a secondary amide. Okay, let's get on to the next slide. Amides. Okay, amides, as we've just seen, have the functional group C double bond O NH2. Okay, so this is an amide. It's different to an amine, and it's really important that you are able to clarify the difference between these two, or recognise them first time. Okay, amides don't need to have a number, just like the carboxylic acids, the acid chlorides. In this case, it's just pentanamide. Esters. Okay, let's have a look at the esters here. Esters have the this functional group here, a carbon double bond oxygen and another oxygen within or inside or in the middle of a molecule. So it has, and an ester has two sides to it. It has the side, the carbon chain that contains the double bond oxygen, and this has the name OH, and the side that doesn't contain the double bond oxygen, and it's just like a branch. Like this is an ethyl, so the name for this is ethyl propanoate. Now esters undergo what we call hydrolysis reactions, so we can break them apart by adding either an acid, a dilute acid. Okay, so this is what the H2O plus represents here. So we add the dilute acid to our carboxylic acid, our ester, and we produce a carboxylic acid and an alcohol. Okay, so we can also undergo this or carry out this hydrolysis reaction using sodium hydroxide. Now the sodium hydroxide here, we can think of it really is, if we take the sodium spectator ion away, sodium plus away, we are left with just OH minus. However, commonly in the exams they'll write down sodium hydroxide or potassium hydroxide. Now it reacts, does hydrolysis in the same way, except for one important exception, and that is that the functional group here is no longer a carboxylic acid functional group, it's a carboxylate ion. Notice the hydrogen is no longer present, it just makes another O minus. And we also have the alcohol that's produced here. Okay, last type of functional group we have to look at is a secondary amide. Here it is here, secondary amide functional group. We don't need to name these. They also undergo hydrolysis reaction in the same way as the esters do. Okay, so we can add dilute acid to produce carboxylic acids and amines, or we can add sodium hydroxide and produce the carboxylic acid and amines.